Hey folks, I'm going to do some pH calculations for you, a little video lecture to help you get through your understanding and maybe even help you with the worksheet. But first slide here is on strong acids and bases. And what's interesting about strong acids and bases is that they have the same concentration. The concentration of a strong acid is equal to the concentration of H plus in solution. When these hit water, 100% dissociation occurs, which means that 100% of the acid molecules split up into ions. So if you have a strong acid like HA, for example, and it's, well, strong, then its concentration is going to equal the concentration of the H plus ions. So with that being said, if I know the concentration of, say, 0.01 molar HCl, then that is the same as the concentration of H plus, which is 0.01 molar H plus ions. This is very similar to is the exact way that I taught it in regular chemistry last year, and probably your best understanding from honors chemistry was a strong acid has the same concentration of H plus as original concentration. Now these are easy to work with, very easy to work with, because all you need to do to calculate the pH is to take the negative log of the original concentration to find the pH, which is the same as the concentration of H plus. In this case, this would be pH of 2. The same kind of rules can be applied to bases. A strong base, we'll call it BOH, is 100% dissociated, so that means that all the BOH that hits water makes OH minus, so for the same reason. You got 0.01 molar NaOH, and you have the same concentration of OH minus. And if you know the concentration of OH minus, you can calculate the POH. Negative log of an OH concentration is the POH, which in this case is negative log of 0.01 is 2. Now let's compare that with the concept of weak acids. Weak acids cannot be assumed to dissociate 100%. And since they don't dissociate 100%, we can assume the concentrations of the acid originally is the same as the concentration of the H+. In fact, it's significantly lower. Weak acids can be their percent dissociation can be determined based on their Ka value. If a Ka value is 1 times 10 to the negative fifth, what that means is that the concentration of H plus times the concentration of A minus in solution is much, much lower than the concentration of HA, which is the original acid. The original concentration is in the denominator is much, much larger than the concentration of the two products together, so you get a Ka that's incredibly small. We're talking about maybe 1% or less than 1% of all ions, all molecules of acid disassociate. Now, all is not lost. We can still figure out the pH of a solution that is a weak acid. We just have to do a little equilibrium calculation with it. So these next things that I'm going to show you have both equilibrium ice tables and pH associated with it.
Into those calculations, I'd like to quickly talk briefly about weak bases. Now, we don't talk about weak bases very much, and pretty rarely do we even do calculations involving Kb values, but it may show up, and so you need to know what they are. So first of all, weak bases have low Kb values. They have a very, very low concentration of OH minus in solution. If this is the general form of the base dissolving reaction, then the Kb expression can be expressed by the concentration of B plus times the concentration of OH minus in the numerator divided by the concentration of the BOH solution in the denominator. And because the concentration of OH is so small and compared to the original concentration of the base, that means that these weak bases have a very, very low Kb value. Now, there are two types of weak bases that I'm going to talk about, and one of them is called an amine. An amine is a molecule, and actually it's a molecule that's attached to the end of a larger molecule usually, that has a nitrogen with a pair of electrons on it. And sometimes it's quite possible that it's a nitrogen with 2 pairs of electrons on the end of it. The prefix amine is something that you probably might be familiar with because of your background in biology. Amino acids are the building blocks of proteins, and typically these acids have N groups attached to them. Sometimes they're long carbon chains with a nitrogen attached to the end with maybe even a hydrogen or something like that. So amine groups are just parts of a molecule that have nitrogen with a pair or two of electrons on it. These have Kb values when put into water that are much, much smaller than 1. Now the next one I want to talk about is the conjugate base of a weak acid. We talked about in a previous slide about the acid and its conjugate base. Now if I take this conjugate base in the form of some salt, maybe instead of just F minus, I plop in NaF into solution and I get Na plus and F minus. The simple presence of F minus in the solution, because it's the conjugate base of a weak acid, HF being the weak acid, simply having F minus ions in the solution drops or increases the pH, and it registers as a Kb value much, much smaller than 1, but it will register. So simply dumping in ionic crystals that have F minus in them, or the anion of a weak acid, basically means that you have a weak base.
This is the example I did in class first and second hour, but it's worth repeating, especially for the people who are absent today or need a little bit of a refresher. So pay attention. Now the first thing that I'm going to pull out of this particular problem is the fact that the pH is 2.38. The pH is 2.38, gives us the concentration. Essentially, if I know the pH, then I know the concentration of H plus at equilibrium, which is a useful thing to know, and I'll explain to you why in a few seconds. But let's calculate the H plus. If you remember from the notes in class, 10 to the negative pH power equals the H plus concentration. So in this case, H plus is equal to 0.0042 molar. Now that's not really useful to us right now, but I'll explain to you how it is useful in a second. Keep in mind that's the equilibrium concentration. So let's set up an ice table. We've got formic acid, which is HCOOH, and it's decomposing in dynamic equilibrium with H plus and its conjugate base, which is HCOO minus. We talked about conjugates and how it's the acid minus 1 proton. The ICE table stands for initial change equilibrium, and the initial concentration is listed for you right here. It is the 0.10 molar solution. That's how much you start with. Originally you have zero concentration of the H plus and its conjugate base. Now I don't know the changes off the top of my head, but I do know that at equilibrium the concentration is 0.0042 molar. So that is for the H plus. So 0.0042 molar goes down here. Now because I know the initial and the final, or the equilibrium, I can calculate the change right here. So this means that this added 0.0042 molar, and if I know one change, I know all the changes. 0.0042 molar, and this is minus 0.0042 molar. Does this look a lot like an equilibrium problem? Well, the answer is yes, it is an equilibrium problem. Last thing you want to do then is evaluate the equilibrium concentrations for the acid and the conjugate base. So I take 0.10 minus 0.0042, and I get 0.0958 molar. And this, of course, is 0.0042 molar. So now I have my equilibrium concentrations of the three, and I can set up the Ka expression and solve for Ka. So remember, the Ka expression is H plus over A minus over HA. So I can put 0.0042 times 0.0042 over 0.0958 and calculate that to two significant figures. And the answer is 1.8 times 10 to the negative fourth. And that's a unitless number. That's the Ka, or the equilibrium constant for this weak acid. Now this next one's a little bit more difficult because we're going to have to use the quadratic formula. What's different is instead of giving you the pH, I ask for the pH and I give you the Ka. I really can't do anything with pH right now because This is a weak acid, so if this is a strong acid, I just take the negative log of this number to figure out what the pH is, but I can't because it's not 100% dissociation. So I have to start with the ice table. The weak acid is acetic acid, and it's in dynamic equilibrium with a H plus concentration and its conjugate base, which is CH3COO minus. So we'll set up the ice initial change equilibrium. It initially starts at 0.30 molar with zeros for the initials. Besides that, I don't have much else. With that being said, I can figure out my changes by determining that the changes are X. Minus X for the initial and for the original reactant, and plus X for the two products. Let's evaluate this to solve for E in terms of X, 0.30 minus X, and these are both X. Now what I want to do is take these and plug them into the Ka expression. Remember, the Ka expression is my products over reactants, so I've got X times X, those are my two products, over 0.30 minus X in parentheses, and that is equal to 1.8 times 10 to the negative fifth. Now if you forgot, that was listed for me up here in the problem, way up at the top. You can still see it here at the very top of the page. Let's do some algebra and solve for X. Let's get all the X's on one side. So I'm going to get this out by multiplying by 0.30 minus X on each side, and then I'm going to use my calculator and distribute this through. If I use the distributive property and distribute this throughout this inside the parentheses, I get 5.4 times 10 to the negative sixth minus 1.8 times 10 to the negative fifth, and that's still equal to X times X, or X squared. So let's rearrange this so that I've got all my X's on one side, and I've got X squared plus 1.8 times 10 to the negative fifth X minus 5.4 times 10 to the negative sixth equals 0. Now I'm going to use a quadratic solver to find my two X's. After using a quadratic solver, I found that my two X's are equal to 0.002315 and negative 0.002333. Now I know this one's negative and X can't be negative because when I plug it into here, up above, my values for X here and here cannot be negative, so I'm going to use the positive value. Let's solve for X. Well, actually we've solved for X. In this case, X is equal to H plus, as I pointed out right up here. So if that's H plus, then let's find the pH. pH is equal to negative log of H plus, so negative log of 0.002315 is equal to 2.64. And it's important to note, and I didn't cover this in this video lecture, but I did talk about it in class, that for pHs, significant figures begin starting at the decimal. The 2 is not a significant figure, so if you want your answer and pH to be reported to two significant figures, you got to go 2 past the decimal.
I want to apologize at this point for writing over the top of the other writing. Hopefully you can tell the difference between the blue writing and the red writing. The blue writing is the correct answer, the red writing is the work. I accidentally edited out part of this video and I can't fix it, so again, I apologize.
Now percent ionization is a little bit different. This question talks about the percent ionization. Percent ionization is essentially defined as how much of the H plus is there in solution compared to the original concentration of HA. That's a times 100, of course, because it's a percent. So if I find the H plus, I divide that by the HA, and I will get the percent ionization. It still requires an ice table, which isn't a problem, but you don't have to do anything with pH at the end. So let's get started. We've got HF decomposing to H plus and F minus. Ice table, original concentration of 0.10 with 0 of these. We've got a change in X of each one of the chemical species, so I've got 0.10 minus X and X and X. I'm going to put X times X on the top because those are my two products over 0.10 minus X and set that equal to 6.8 times 10 to the negative fourth. Using algebra, I'm going to rearrange this so that 0.10 minus X is over here, and I'm going to distribute to find out that my two answers are 6.8 times 10 to the negative fifth and negative 6.8 times 10 to the negative fourth x. That's still equal to x squared, so let's rearrange this so everything's on the same side. 6.8 times 10 to the negative fourth x minus 6.8 times 10 to the negative fifth x is equal to 0. Again, I'm going to pull out my quadratic solver and find my two x's. The answers I get are 0.0079 and negative 0.0086. So again, I can't use the negative values, so I'm just going to toss that one out. I'm going to take this, and that is the concentration of my H+. If I plug it back into the ice table, that is X. So if that's X, then that's H+. So if I want to find percent ionization again, I do H+ over original concentration of the acid. In this case, it's 0.0079 divided by the original concentration of 0.1 times 100 to get percent ionization. And the answer I get is 0.079%, which means that only less than 1% of HF actually makes it to ions, based on the Ka value, which is not a lot. Pretty weak acid. Now, the last calculation we're going to talk about are called polyprotic acids. Poly means more than one, and protic refers to the number of hydrogens. So polyprotic acids have more than one hydrogen in the substance. This complicates things a little bit because you essentially have two Ka values. You have a Ka1 and a Ka2 and a Ka3, depending on how many protons are. Each proton has a value, a Ka value, which represents its likelihood or its acidic value. Now, some have polyprotic acids, and the first one is really, really high. And every one after that is subsequently lower. Now, if you have a triprotic acid like H3PO4, for example, the third is going to be the lowest of them all. And this is a pretty common and important observation to make about polyprotic acids. Some polyprotic acids are always weak, meaning their Ka1 is weak and so is their Ka2, but some have a very strong first and a weak second. An example being H2SO4. The first one is much, much greater than 1, and the second one is 1.2 times 10 to the negative second. So the first one is strong, and the second one is actually pretty weak in comparison. So it's possible to have one strong and one weak, or in H3PO4's case, all of them very, very weak. If you wanted to know the exact amounts, it's 7.5 times 10 to the negative third for the first one. The second one is 6.2 times 10 to the negative eighth. And its final one is even lower yet, 4.2 times 10 to the negative 13th. The first one's, basically it means the first one's is not likely to leave, but would leave. The second one is not very likely, and the third one's even less likely. So in solution, it kind of hovers around, it's mostly H3PO4, but some H2PO4 and some HPO4 and very, very little PO4 minus.
3.
So we're going to talk about doing calculations with polyprotic acids, and you might think it's really, really complicated, and they are, unless you make some pretty significant assumptions. And this is right from the book. I'll read it for you. As long as the successive Ka values differ by a factor of 10 to the third or more, it is possible to obtain a satisfactory estimate of pH of polyprotic acid solutions by treating the acids as if they were monoprotic, considering only the first Ka as the only Ka. And in this case, the first and second Kas are bigger than 10 to the negative third different. So we can essentially say that this is so small that it's negligible. And really, if we're going to do any calculations involving this polyprotic acid, we'll just simply use the first one as the only one, which really simplifies things a lot. So we'll still have to do an ice table, and we'll still have to do some quadratic solving, but it's not more than that. Similar to the last practice problem I just showed you. So let's set up the ice table. H2CO3 dissociates into H+, and its conjugate base, which is HCO3 minus 1. Initial change equilibrium. Initially 0.0037 molar with initial 0, change minus x plus x plus x. You've done this now a bunch. You see this can be done pretty quickly. Let's put in x times x over 0.0037 minus x and set that equal to the Ka, which is 4.3 times 10 to the negative 7th times 10 to the negative 7th. I'm going to share with you a little something that's going to make these problems go a lot faster for you, and it's an assumption that we can make that will eliminate the use of the quadratic formula. And I want you to pay close attention to this x right here. We're going to assume that the amount dissociated, or the percent dissociation, is very, very small. And that means that this number that I just pointed to, and I'll point to it again, this x on the denominator is so small compared to this number that we can essentially treat it as negligible. And so if I rewrite this, assuming this x is really small, my quadratic formula, or my Ka expression sets up like this. Without the x in the denominator, that's still equal to 4.3 times 10 to the negative 7th. And I'll explain to you, we'll execute this problem, solve for x, and I'll explain to you why we can do this. So by eliminating the x in the denominator there, and we rearrange this to solve for x, so that x squared is on one side, you get x squared is equal to 4.3 times 10 to the negative 7th times 0.0037. When you multiply those together, you get a really, really small number, and if I take the square root on each side, x is equal to 3.99 times 10 to the negative 5th. Now that we've got that x value, as long as this number, which by the way represents the number of the amount of H plus in solution, even though we assumed that's very, very small compared to the original concentration, and it is, as long as the percent ionization is less than 5% of the overall, then we can assume that the amount dissociated is so small that the original concentration is a satisfactory amount, and I'm pointing to it 0.0037. So let's just take this quick, 3.99 times 10 to the negative 5th divided by 0.0037, and I already know that this is going to be a really, really small percent ionization, but let's do it anyway. The answer is 1.1%. So that means that this acid dissociates only 1.1%, and that's a small enough amount to basically be negligible for the denominator right here. Let's point at it again. Now it's still important that x is in the top, but it's not important that x is in the bottom, and that really saves us a lot of time when doing quadratic formula. And you can essentially just assume right off the bat that x is negligible down here, do the calculation, and then go back and check after. Most of the time x is going to be small enough compared to the original concentration where it will be negligible. But if it is bigger than 5% ionized after you've done the reaction and you're finished and you check percent ionization is greater than 5%, then you actually have to go back and redo it and do it with the quadratic formula because it will make a difference. But anyway, let's go back to my calculation. I've calculated x to be 3.99 times 10 to the negative 5th, so that is the concentration of the H+, and if I take the negative log of that number, I get the pH, which is equal to 4.40. I want to use two significant figures here because my original concentration was only two significant figures, so my answer can only be two significant figures, which is just 2 digits to the right of the decimal on a pH.
That takes care of this video lesson on pH calculations. Thanks for listening.